your crystal field stabilization energy, it leads to some many abnormal things in your complexes. The first abnormality that we see is in the lattice energy of the complexes. Lattice energy, we know, is directly proportional to charge and inversely proportional to size. That is, as the charge increases, the lattice energy increases, and as the size increases, the lattice energy decreases. So, if we talk about our M2 positive metal cations of the 3D series, like your scandium 2 positive, titanium 2 positive, and so on and so forth. So, on going from left to right in this, that is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. On going from left to right, all of these are 2 positive, that is, all of them are present in complexes. On going from left to right in this, what should happen is the lattice energy should increase. The lattice energy should increase because on going from left to right, the size is decreasing, as we know from our periodic properties. The size decreases on going from left to right, so lattice energy should increase. So, if we draw a graph, that is the x axis and the y axis. On the y axis, you have the lattice energy, and on the x axis, you just have your metal cations. So, the lattice energy should have increased, and we should have gotten a straight line like this, with everything lying here: calcium, scandium, titanium, vanadium, chromium, manganese, and so on. But when we observe the actual values of your lattice energy, what graph we get is actually this. Let me just draw it in another color. So, this is the graph that we actually get. The red one, the red line is your theoretical line. The blue line is the observed line. Why this happen? This happens because of CFSE. The lattice energy, that is the observed lattice energy, is equal to the theoretical lattice energy plus CFSE. Now, higher the CFSE a complex has, higher is going to be its lattice energy. For example, here at the top lies vanadium 2 positive. Here at the bottom lies manganese 2 positive. Okay, and here again lies Zn 2 positive, and again at the top lies Ni2 positive. Why? Because vanadium 2 positive has the configuration 3D3, Ni2 positive has the configuration 3D8, Mn2 positive has the configuration 3D5, and Zn2 positive has the configuration 3D10. We have already calculated the CFSE in our previous slides. From the calculation of CFSE for the high spin complexes, you would know that the CFSE of the D3 and the D8 comes out to be the highest. That is why the lattice energy of the vanadium 2 positive ion and the Ni2 positive ion, it comes out to be the highest. And when we calculated the CFSE, we also saw that the CFSE of the D5 high spin as well as the D10 configurations was 0. That is why manganese 2 positive and zinc 2 positive, they lie on the actual line, because for them the observed lattice energy is equal to theoretical lattice energy, because the CFSE is 0. For zinc also, the observed lattice energy is equal to theoretical lattice energy, because again for zinc CFSE is 0. For others it is not so. So, scandium lies here somewhere, titanium also here, chromium also lies somewhere here, as well as Fe2 positive as well as CO2 positive, and here lies somewhere Cu2 positive. So, this is how the CFSE or your crystal field stabilization energy is determining the values of your lattice energy. That is how it is affecting the lattice energy values and how it is causing an abnormality in the trend that we expected for the lattice energy value. This, however, is not just concentrated to lattice energy. This same trend and this same abnormality is also shown by hydration energy values. Again, hydration energy is directly proportional to charge and inversely proportional to size. So as we go from scandium to positive to zinc to positive, it should have been again a straight line going upwards. This is the hydration energy, this is the metal ions. So it should have been a straight line going upwards. But it is not so. Again we get a hill-like structure. This. And what is happening here? Again lies at the top vanadium 3 positive, and here 2 positive, here nickel 2 positive, and here Zn2 positive, here we have Mn2 positive, and here we have Ca2 positive. So Ca2 positive also has CFSE 0 because it has no d electrons at all. So Ca2 positive is actually d0, that's why CFSE is 0. So Ca2 positive is also going to lie on the line. And here we will have scandium 2 positive, titanium, then we have chromium 2 positive, Fe2 positive, CO2 positive, and Cu2 positive. This again, the reason is that the observed hydration energy is equal to the theoretical hydration energy plus the CFSE. As the CFSE increases, the observed hydration energy increases. That is why for vanadium 2 positive and Ni2 positive we get the highest hydration energy, whereas for Mn2 positive and zinc 2 positive the hydration energy is equal to the observed hydration energy because there is no CFSE. Similarly for Ca2 positive also, Ca2 positive is D0. So that is why also it has the CFSE equal to 0. Now another thing, if we instead of taking the M2 positive ions, we take the M3 positive ions. Then again we are going to get a hill-like structure. That is, this is the theoretical lattice energy and the observed lattice energy will again have these values. But here you are going to have one more abnormality. This is CO3 positive. Now why does CO3 positive have such a high CFSE? CO3 positive has such a high CFSE because if you remember H2O used to show dual behavior. With all the other metal cations of the 3 positive type in the 3D series, it behaved as a weak field ligand. But with CO3 positive, H2O used to act as a strong field ligand. If it's a strong field ligand, then its value of del O is going to be high. And if the value of del O is going to be high, then the CFSE is also going to be high. That is why with CO3 positive, it gives an abnormal value, and that is why the size of the hills are changing. Earlier, vanadium 2 positive and nickel 2 positive were present equally. But in this case, CO3 positive increases the size of the second hill. And you can calculate this, and this scandium 2 positive will be present now. Because scandium 3 positive is going to be D0 now. And similarly the others also, but the main thing is that the CO3 positive is an exception in this case, because hydration energy is what? Hydration energy is basically water molecules surrounding your metal cation. And the water is going to act as a strong field ligand for CO3 positive, which leads to this behavior. Now let's look at another abnormal behavior because of the crystal field stabilization energy, which is the abnormal behavior of the D7 octahedral complexes with strong field ligands. In this complex, cobalt is in +2 oxidation state. That means its electronic configuration is 3d7. This complex, it readily gets oxidized by losing an electron, so that cobalt becomes in +3 oxidation state, 3d6. How does this happen? First of all, the NH3, because of NH3 there is going to be no pairing. So first of all, the electrons are going to be high spin. So 1, 2, 3, 4, 5, 6 and 7. Then this electron which is present in Eg, it comes and it pairs up with the T2G. So that the configuration we get is Eg1 and T2G6. So now this is T2G6 and Eg1. So the Eg1 electron, that is this electron, it readily goes out of the complex and it oxidizes the complex. So that is why the CO2 positive in the 3D7 configuration turns to CO3 positive in the 3D6. Now stronger the ligand, more pronounced this effect is going to be, and this is entirely because of this CFSE. Because the del O is high, so the CFS is going to be high, and higher the del O, more easy will it be for the electron to go out of the complex, and more easy is going to be the oxidation of the D7 octahedral complexes. So these were all the abnormal behaviors shown by your complexes, octahedral complexes, because of CFSE.